Yep, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Try it again. This should work. Here, let me cue this. Here, I'm in front now. Awesome. Okay, so do you want to turn it? Is there a way for me to see the crowd with your webcam? Okay, so I've cut the audio from the Hangout. Okay. Perfect. No, this is fine. Okay, good. So you will notice that there's a 40-second delay. That chair is awesome, by the way. I know you'll hear this in 40 seconds, but the chair is fantastic. Good. Okay, so let me start by talking a bit about the security of Android here. So for those of you who are watching this a bit later on live on the internet, it's going to be a bit kind of weird for you guys. But I'm actually watching a crowd right now, and they're listening to my conversation. And one of the weird things that's happening right now is I'm actually hearing my own voice loop back into my earpiece. So what I said 40 seconds ago is playing in my ear right now. I'm going to try to ignore my own self, but I might have to ask you to actually mute the audio at some point, okay? Because your loudspeaker is actually playing back in the Hangout, and so it's a bit odd for me as well. Okay. Android security internals. So Android security is pretty complex, and there are quite a few moving pieces. And what we're going to do here in the next hour or so, we got 54 minutes to go, is to actually go through the various parts of the stack. And effectively what we will do is take them apart one by one and try to address questions as they come. Okay? So, oh, thank you, Klaus, for muting my own voice. This is awesome. This is even better. Just a general note about the slides, and I will put them up again after the presentation. So I've taken material from various different places, okay? And if anybody out there doesn't feel comfortable with our use of their material, they just need to let us know, and we'll take it away. So I know that there was some documentation that had been sent out regarding a bit of my background, but just in case, so I wrote the Embedded Android book for Riley, wrote the Embedded Linux book for Riley, have been doing open source for quite some time, which doesn't mean that I know everything, but I try to at least steer people in the right direction. So what are we trying to talk about here in terms of security? So you'll notice actually that within my lineup, we don't get to Android until quite a bit far in my presentation. That's because there's a lot of things that happen under the hood, and Android needs those things to actually operate and provide good security. So if at any point in time, you want to understand Android security, you'll usually have to go back and actually look at the hardware that is underneath it. And before I start proceeding, actually one more general administration note about the technology we're using. If at any point in time somebody has a question and you want to voice it, kind of speak the question, just unmute it, and unmute your laptop, and you should be able to ask a question via Hangout. Another way to ask me questions is via the chat on the YouTube channel. So since this is playing off of YouTube, if you have a mobile device or if you've got a laptop, you can just go to the chat and put a question there. I'm able to actually see it. I've got 2 monitors in front of me here, and I should be able to pick up your question your questions as they come. Okay, the chain of trust. So effectively what we want to do is ensure that the operation of the system from the get-go, from the moment we flip the power switch on until we're talking to the cloud, is secure. And in order to ensure that, we have to have a chain of trust. We have to start from a known good place, from the silicon that we trust and images that we trust and so on. So this is a very key thing that's going on here, and you'll see this actually coming back in my slides several times. The first thing we need to understand is the silicon that we're working with. So this is a diagram that I've used throughout presentations that I have around. So we have an application processor, and in the case of a phone, a baseband processor, and the application processor is running Android. And the question is, how is this secured, and how is this made sure to run known good images and such? And this is a quote that I really like. It comes from Ken Thompson, so one of the co-creators of Unix. And he did a paper for receiving a Turing Award in 1984. And what he did is he actually modified the compiler so that when it compiles a program, it actually injects into the program effectively malicious code that is self-replicating. And the quote that he has is pretty interesting. You can't trust the code that you did not totally create yourself. No amount of source level verification or scrutiny will protect you from using untrusted code. In demonstrating the possibilities, I used a compiler. And then he says, as the level of the program gets lower, these bugs will be harder and harder to detect. And effectively, if you are able in some way, shape, or form to get something into the hardware, the software will have a very, very hard time actually seeing this. And if you don't believe me, what I did is I put a bunch of pointers here in these 2 next slides. And as I said, the slide set will be available later. I'll make sure Klaus gets a copy so he gets it to you guys. You've got a bunch of things here. I'll mention not everything, but I'll mention a few things. So the JTagulator, very interesting device. What it does is it has a bunch of screw leads on it, and you can screw in a bunch of wires. And if any of these wires are part of a JTAG interface, then it will come back and tell you, okay, wire 15, 13, and 5, and 6 are a JTAG. And then you can use that to actually start doing and it will tell you which JTAG pin actually. So you'll be able to use that to then actually talk to the processor that's there. So just effectively hiding your JTAG by not soldering a header or not marking it on the silk screen on the PCB or whatever is not protection. You have to have other ways of protecting JTAG, either by disabling it completely in the chip when you ship it, or just not exposing those pins in any way, shape, or form. Bus Pirate is another interesting thing. So effectively, you can plug in an I2C, an SPI, or whatever bus on this, and then you can interface on the other side of that board with your PC. So you can either use that to read stuff off or inject stuff in. So effectively, if your driver, for example, in Linux assumes that the hardware it's talking to gives you values from range X to Y, and then this one comes with Z because it's just completely out of bounds, your driver might actually fall on its face, and this might actually be used to analyze the software that's going on. And there's more fancy stuff here. For example, there's DDR analysis tools. I mean, if I could desolder a chip from the board, there's nothing that precludes me for effectively adding some interface layer that reads what's going to the RAM and then just buffer it and do whatever you want with it. So effectively, if it's going out of the chip, you have to assume that it is non-secure. It's non-trustable. A whole bunch of other things here, like, if you go to AliExpress, you'll find some tools that allow you to do some data recovery off of handsets. Effectively, you can unsolder an eMMC off of one of those phones and then effectively have a device read the content of that and then do whatever you want with it. Face Dancer, this is an interesting thing. It allows your PC to act as a USB device, and so you can effectively plug in another PC or whatever else on the other side, and then do some funky stuff with Python and so on. And there's a whole bunch of different things here that have been tried over the years. So in other words, you have to assume that your hardware may be hacked at any layer. And obviously, there's one I'm not covering here yet. I'll talk about it later, is attacking the chip itself. And that too is another level of attack. But let's, for the sake of conversation now, just assume our chip is secure and then see what happens afterwards. So if we assume the hardware is secure, then in the software side, there's a whole bunch of things that have to be secured, starting from the early boot software, going to the trusted execution environment, TrustZone and so on, then Linux and Android, and all the way up to the cloud services and OTAs that come afterwards. So this is a generic architecture of diagram architecture for Android that I've been carrying over through the years. It does a fairly good job of explaining to you what is where in the stack. And I'm not going to go through this in great detail because we don't have the time to do that. But let's just say that there's a whole bunch of security mechanisms that are added in this throughout. So there's mechanisms in the kernel, there's mechanisms in the native user space, in the system services, and then in the control of the applications that are running on top of all that. Okay, speaking of system on chips, so we kind of took a more holistic approach kind of high-level overview of the system earlier on. Taking a look at the chips themselves, let's start taking a look at what's inside and what they provide us in terms of capabilities. So in a system on chip, you'll typically have a whole bunch of subsystems, and the core, which typically in the case of Android is going to be ARM, is going to be connected to some form of interconnect to other components as well. And so the security is going to have to be integrated in a whole bunch of different parts of the system, and most importantly, the interconnect. And in the case of ARM processors, this usually is one of the variants of the EXI interfaces or buses. And so if you start reading deeper into ARM architecture, you'll find a lot of literature about this stuff. Other things that you will have in a chip is crypto parts. You'll also have parts that are burned onto the chip from factory. So this is a diagram that I got from an ARM presentation, and it might be a bit tiny here for you guys watching from afar. I have several of them, so just bear with me as I kind of walk you through this. I guess you'll at least visually see that there are some blue boxes, some white boxes, and some shaded boxes. So the idea here is that within a chip, you have parts that are known to be secure, and parts which are known not to be secure or can transition from security levels between non-secure to secure. So for example, you've got a trusted boot ROM. So this is a boot ROM that is on the chip itself. And when the chip boots, it boots from that boot ROM. And then that boot ROM's job is to ensure that the subsequent software pieces that are running are also secured. You'll also have some eFuses. So these are effectively fuses like you can think of as a general fuse, when you kind of burn a fuse and you have to change the fuse. But in this case, you can't change the fuse. Once you've burned the fuse, which effectively happens by applying a certain voltage on a certain connection in the chip, you burn it, and once it's burned, it cannot be unburned. And usually eFuses are going to be used to actually, from factory, program the chip with certain things, be it constants, and in the case of secure boot, as we'll see later, what we will burn in there effectively is a hash of a certificate, a root certificate. And this hash will be later used to ensure that the root certificate checks out. And then once that root certificate checks out, that will be used to ensure that the rest of the boot is secure all the way into Linux. These eFuses here are very, very important. You'll also have other things that could be burned there. For example, JTAG state, whether JTAG is enabled or not. You can burn an eFuse to effectively say, okay, no JTAG is enabled on this chip. So therefore, once somebody gets the device in the field, even if they try to connect something over JTAG, it's totally useless. Right, here's another view. Box is a bit bigger, but I'll still assume that this might be tiny for everyone. You'll have the chance to look at these in more detail if you want when you review the presentation once I make it available to you. But effectively, same kind of a distinction being shown here. So you've got these dark colored boxes which are known to be secure, and the white ones which are not secure, and then some of them which can be of the two kind. You'll also see here that there's some SRAM, so there is RAM on the chip itself, and so this RAM, which is could be called on-chip memory or OCM, is usually going to be the place to run the TrustZone and anything that is supposed to be secure, because then it's not going off to the external bus, and therefore it can be trusted during the lifetime of the system. Now, one thing that is very important for all this security and non-security to happen is that the interconnect, and that's a very, very key concept here, the interconnect that's in the chip carries over on it whether the access is secure or non-secure, all right? And so at boot up, you can configure different peripherals to be either secure or non-secure, and then when an access comes on the bus, it will then go, it will only be allowed if it has the proper security level. Well, how is this being used? This is primarily used in the case of, say, for example, TrustZone. So when the processor is running in TrustZone mode, which I'll describe a bit later, the access, any access coming off the bus is going to be known as secure. Whereas if the processor is running plain Linux, the access comes out as non-secure. And therefore, there are things that will be available to the core, to the ARM core, when it is running in TrustZone mode, that will not be available to it if it is not running in TrustZone mode. The other thing that can happen with this segmentation of the memory is you can actually segment the segmentation of the security. Sorry, is you can segment memory such that some regions are accessible only to the secure software, and others which are available to non-secure software. And really this is a case where effectively under Linux you can have things that are running that it can't see, all right, because they're in this protection mode that the processor switches in that Linux just doesn't make available. And so this would be the software architecture that you can lay on top of what I just showed you in terms of hardware. So I'm going to start with the ARM32 case because it's a bit simpler, and then we'll get to the ARM64. So in the case of the ARM32, you have a non-secure mode and a secure mode, and those two things are completely isolated from one another, and this is baked into the instruction set of the ARM processors. There's no way for Linux to cross this barrier. It's totally invisible to it. The trusted environment, the trusted OS, and the trusted applications, Linux doesn't see them, can't in any way, shape, or form get access to them. So when an application wants to talk to a trusted application on the other side, the way this is usually routed is you have an app talking to an operating system driver, and then the operating system driver makes a call into the secure monitor. The instruction for that in ARM is called SMC, secure monitor call, and effectively what happens there is the core, the ARM core, is that they're going to save state for registers and stuff, switch in the trusted hypervisor or trusted execution environment, and then that trusted execution environment will route the call to the trusted application that is being talked to. And then in reverse, when the application responds, it goes the other way around. In the case of ARM64, it's kind of just a bit more complicated. They added a level to this thing. They added this thing called the ARM Trusted Firmware. And the ARM Trusted Firmware really actually is now under the trusted operating system, and you could actually have multiple trusted operating systems running side by side. Some phones are rumored to actually ship with that, and the only reason I know this is because some people did some reverse engineering on these phones and found hacks and stuff like that, and discovered that, hey, wait a second, this phone actually ships with 2 trusted execution environments. So again, this is a case where we are dividing on the software side. We're creating a barrier using the instruction set that says non-secure software can't see secure software, and the way we enforce that at the hardware level is you actually have a bit that is carried over the address bus on AXI and says, okay, this is a non-secure access or this is a secure access. And this is kind of a richer kind of view of the system where you see the normal world here. So this is, say, my Linux stuff in the green, and then you have the trusted world with the ARM trusted firmware, and then the boot process that is happening here, where you have a first stage bootloader loading a secondary boot stage bootloader, and then loading trusted operating system, trusted firmware, which then actually gets us into Linux, and obviously Android on top of that. All right. Okay. So that's the architecture of the, yes, I saw 2 questions here. So, hey Kareem, some of the audience from your training at Bosch here. Nice to see you again. Sounds like the setups. Yeah. Klaus, I can hear you. Okay, so will I notice that there is time missing if I'm using an application? You probably would. Yeah, I'm switching audio here. I've got 2 mics, okay? And effectively, when I'm going to answer the questions, I'll answer them off of the YouTube live stream, and I'll shut the other mic off. But I'll put the other mic off if I need to actually have a real-time interaction with you, okay? But in terms of time, so the time issue is probably real. I don't know if you can actually accomplish something with that in terms of knowing, you know, when you switched over and came back. I assume you could probably know that there's time gone, but you wouldn't know whether this is because of the trusted execution environment or just because the operating system took the scheduling away from you. I'm not sure the application would be able to see that. I think the operating system might actually be able to time how much the trusted execution environment takes to actually answer back. Like, for example, I take the time, I make an SMC call, check the time again, then I will know exactly how much that SMC call has taken. But otherwise, the application, I'm not sure that it would know and derive any information from the fact that there is, hey, time gone. And if you could be so kind to shut the loop back into my ear, if that's okay with you, so that I stop hearing myself speak in my own ear. Yeah, okay, and then I'm going to right away pick up the question from the chat, which is about the Spectre and Meltdown. Is this setup susceptible to Spectre and Meltdown? Yes, of course it would be. But this is actually part of the side channel stuff that I'm going to be talking about right now. Okay, so what can I actually do in terms of vulnerabilities? So as is actually asked in the chat right now, one of the things that is possible is side channel attacks. Cache attacks, timing attacks, power monitoring attacks. Those are real. Okay, those are real things that you can actually make happen, then you have to have mitigation for this. Some chips, and you can research this a bit. Some chips actually go above and beyond the call of duty. Some chips actually have the ability to detect that you are actually trying to perform some of the stuff, or they have countermeasures to actually alleviate the issues. So, for example, some chips will be able to tell you that they're uncapped, and then do whatever it is that's required in those cases. Because decapsulation is a real possibility. I mean, if you go look at the stuff Bunny Wong did in the early 2000s to reverse engineer the Xbox, that's what he did. He uncapped x86 chips and then started taking pictures of them, which is kind of interesting. But this was a single guy having access to a lab at MIT. We're 20 years almost later on. Assume that any, say, nation state has more than enough capabilities to pull some of this stuff off. So it depends on what you're trying to accomplish here and what you want to secure. Generally speaking, for a consumer device, most of the chips that we have here should be okay, all right? But the easier ones are like probing available pins, right? If you've got pins that are exposed, JTAG, all right? Which gets me to secure booting. So now that we understand a bit more about the hardware that we are interfacing with, let's take a look at how the system boots from the get-go. So this is a diagram that I put together based on what I had found and researched, and it's a bit complicated, but I'll try to make it as simple as possible. Let me just start by walking you through the basics. So we have a chain of certificates which are used to sign images, all right? The manufacturer, the OEM, effectively the company that is using a certain chip from a certain vendor to create a certain line of devices, they're the OEM here, and they create a root certificate. They use that to sign an OEM attestation cert, and then use those to actually sign OEM attestation certs, CA certs. So yeah, so effectively there's a chain of trust happening here that the OEM owns. All right. And then the OEM is going to take the hash of that root cert and they're going to burn it in the eFuse of the system on chip. So then the system on chip arrives from factory with a hash of a master cert. And then whenever some software wants to run, it'll first check that the master cert validates. And I'll walk you through that in a second. So my system on chip, and I'm just highlighting 4 parts of it, has eFuses where I burn these hashes and other things. I have a primary bootloader, which is on the chip, so this is in the ROM of the chip itself. I have some crypto capabilities, and I have TrustZone capabilities here. So when I flip the switch to on, all right, my SoC comes online, and then it's going to start booting that primary bootloader. The first thing it does is a built-in self-test, effectively a hardware thing that goes around and checks that everything is behaving properly on the chip. And once it's got that, primary bootloader loads. Primary bootloader's job is to boot the secondary bootloader. How does it know that it can trust the secondary bootloader? That's where those certs come in. So there's a root CA cert hash in the eFuses. The secondary bootloader has effectively this certificate chain, and then the primary bootloader is going to grab this, and then going to check that it's properly signed. And once it knows it's properly signed, then it knows that it can trust this chain, and then it's going to use the certs here to check the secondary bootloader. And once it knows it's good, it boots it. And then the job of the secondary bootloader will then to actually boot something like little kernel and a trusted execution environment, which is going to be what's going to be running on TrustZone. Little kernel here is one of the bootloaders that is used for Android. It's not the only one, and several vendors actually use their own, but it is the one that Google usually uses in their devices, and there are some vendors that actually use it as well, although some more recent devices might be using other stuff. So this is just the start of the boot process. Now let's take a look at what we are actually booting. What's this little kernel thing? And I'll mention it again later on. So there's an upstream little kernel project that's on GitHub. And effectively, you can go get that if you want to, but it is an executive. It doesn't have any specific bootloader functionality. However, SOC vendors will take that, they'll add their own stuff and make it a bootloader out of it. And then effectively, the SOC vendor, I don't know, Qualcomm or whomever else that you're using, will then actually give a BSP to an OEM, and then the OEM will take that, sign it with their key, and then create an image that is bootable. Again, the OEM signs it with their key because it matches their certificate chain, and that's going to all mesh into this checking of the certs as they go. Another thing another image that we might be booting is the trusted execution environment. So the trusted execution environment, or TEE, comes from one of the vendors that I'll mention later on. There are 2 open source ones that I know of, and also I'll document those as well. And the upstream TEE effectively is used by the SOC vendor, customized again, given to the OEM, and then the OEM signs that too with their key. And you can see here these crypto keys are being used all over the place to make sure that the images coming in are all checked. The root of it all, again, comes from the eFuses. The eFuses have a hash, and the hash is going to attest to the validity of the OEM root CA cert. And this chain here, the actual cert is not on the chip. The actual chain here is going to be in the secondary bootloader, but the primary bootloader can check that this chain is valid because it can use the hashes and the eFuses to make sure that the incoming stuff is good. All right, so this is how we start a trustable boot flow. And so this is another view of the boot flow from ARM itself. I didn't like this one as much because it doesn't show you the cert. To investigate this is, okay, all this thing about trusting software is cool, but how do I know that my software is running in a controlled fashion or that I can trust where it is running from, okay? And so this is where the execution location matters. And so the primary bootloader or firmware is going to be running from a specific ROM or RAM, and then you're going to have the secondary bootloader, first stage secondary bootloader, and then the TrustZone. They're all going to be running from on-chip memory. So in other words, they're running on the actual chip itself, not outside using the RAM, but really inside. And then effectively the other bootloaders, like for example little kernel or U-boot or whatever else, they're going to be running from system RAM. So they're running outside the security zone. But the TrustZone is running in the on the chip itself, and therefore that makes sure that you can trust the TrustZone software that's there. Again, if you go back and read some of the stuff I mentioned to you, of course, if you were to decapsulate the chip and have the proper gear, then maybe you can screw with this. But generally speaking, the on-chip memory should be considered safe and secure. Connection dropped. Put at startup boot flow slide. So let me know if you're still having hardware issues on your or streaming issues on your side, and I'll repeat. But I'll judge from the body language and the fact that Klaus hasn't interrupted me that we are good. Okay. Speaking of little kernel, so little kernel, as I said, is not mandated by Google. It is, however, used on some devices. Oh, there we go. We got a thumbs up over there. Thank you. So the original little kernel is at GitHub. So GitHub little kernel wiki, and go check that out. It's a small thing. It has almost no traces of Android functionality in the main project itself. And you can have a look here. Okay, there is a sample little kernel from Linaro that contains some of the goodies that you might be looking for in terms of Android-ish. Oh, no? You got an issue? This is going to be awesome. More of it. I should be able to follow up with that. Okay, so here's this is actually a detailed explanation of the boot process for the 410E board, which is an open source board that Qualcomm put out. So if you want to check, kind of like a detailed walkthrough with little kernel, this is a good starting point. All right, which gets me to locked and unlocked. So this idea of locked versus unlocked bootloaders, it really is an artificial distinction, and it really is dependent on the OEM. So the OEM can say, I want to have the ability to provide users to unlock or run unsigned images. That's up to them to decide. But there's nothing in Android specifically that plays with this, except the verified boot stuff that you might see in the documentation. And the hardware itself doesn't have any notion of this locked versus unlocked state. However, it is very possible that the bootloader might actually give the locked versus unlocked state to the trusted execution environment, and then the trusted execution environment can keep that in mind and later make decisions based on that. So for example, some trusted applications may decide not to do some playback or decode stuff for you unless you are actually running a formally locked, an AKA properly signed image, and otherwise not give you access to that. So that's for little kernel, which gets me to TrustZone. So we've spoken a bit about the boot process. and you know, we're getting close to booting Linux here, but we're not there yet. One of the key things that we want to boot very early on is a trusted execution environment. In other words, an operating system that's going to allow me to run trusted applications. Now, the trouble that there is with TrustZone is there isn't a lot of information that is publicly available about it. A lot of it is hidden behind NDA curtains. So it becomes a bit hard to get, you know, start playing with it. If nothing else, just to study it, understand what's how it actually operates. And the other thing that you will find difficult is sometimes the chips that ship actually ship with TrustZone disabled. So in other words, you can't actually use the TrustZone functionality because the chip doesn't have it enabled. So that too is somewhat of an issue. One organization that has tried to do a lot to actually alleviate the pain of working with TrustZone is Linaro. So these are 2 pointers that I recommend taking a look at. So they have instructions on how to actually run a TrustZone in an emulator, in a QEMU, and they also have Opti, which is one of the TEs, one of the TrustZone OSs, running on the high keyboard. So that's another avenue that you can look at. So how are we doing on time? Okay, we're about we got about 20 minutes to go. So I'm gonna have to speed up the pace here because I've still got quite some material. So okay, hardware backing. This goes back to what I was mentioning earlier. TrustZone to operate properly requires the secure versus non-secure bit that I mentioned, and it relies on internal memory to operate properly. So it runs on the chip itself. Here's another, again, diagram of an ARM chip. So green stuff is non-secure, the pink stuff is secure, so trusted boot ROM is secure, trusted RAM is secure, on-chip fuses, one-time program fuses are secure, and then you've got stuff which is configurable. It's probably going to be hard for you to see this on a projector, but there's like 2 kinds of greens, and effectively some of these things can be configured as you know, secure, and other ones non-secure. All right. Secure monitor call. This is an instruction part of the ARM instruction set architecture, where it effectively allows us to switch from the regular OS to the trusted execution environment. So here's a good diagram showing this. My Linux effectively calling through a driver into the trusted untrusted firmware, which dispatches the call off to the trusted execution environment, which then dispatches it off to the trusted application. All right. What services does the trusted execution environment provide? It's an operating system like other operating systems. So we have here scheduling, inter-process communication, communication with the high-level operating system, and so on and so forth. All right. So this is really a completely separate operating system. All right, from Linux and from Android. So the only way Linux and Android can talk to this thing is through the SMC call that I've been covering since the beginning of the presentation. Some of the trusted execution environments on the market, the 2 main commercial ones that I was able to find information about or know that they existed, are the Qualcomm Secure Execution Environment, and then the Trustonic or Kinibi one, which also is another trusted execution environment. Interestingly, there are 2 open source implementations, TrustT and Opti. So TrustT is maintained by Google. And you can get it off of their own website. It is based on Little kernel. That's the same Little kernel that I mentioned earlier is used for Android bootloaders. And you've got Opti, which is also open source and seems to be maintained by folks at Linaro. And effectively, this one even has more information out there about it, I think, than TrustT in certain regards. Which gets me to trusted applications. So trusted applications are an app, you know, not so much like a touch app in an Android environment, but it is actually kind of like a program, right? So effectively you have a trusted application programs that can be shipped either from factory on the system or could possibly be loaded over the air onto the device and then run based on their signature on the trusted execution environment. And my understanding from the literature I was reading that it seems that certain Android apps could have trusted apps in them that are then loaded onto the TE and run on the fly. All right. One interesting thing is the rich execution environment communication. So REE stands for rich execution environment. And effectively, it is the communication between the trusted applications and Linux, or effectively, you know, whatever's on the other side, of the trusted execution environment. This is usually going to be done using a driver, and there might be even a daemon on Linux or Android that actually talks to this driver. And I'll show you examples of that later on. You'll see how some of the key Android subsystems actually interact with the trusted applications. One very interesting aspect that for me kind of like took actually quite a long time to piece together is how we securely store stuff. Because if you read the Android documentation from Google, they'll say, okay, the key store has to use a hardware-backed storage, but then they don't actually tell you how this hardware-backed storage works. You know, how are we storing these keys in a secure fashion or whatever else? And so after reading quite some stuff, I eventually landed on this thing called replay protected memory block. So effectively eMMC or SD cards, the spec of that has this capability called RPMB, and effectively this is what is used to secure the communication between the SoC and the storage. All right, and the way this works is on the chip from factory, you're going to use a one-time programmable HUK, HUK standing for hardware unique key. So in other words, you're going to just generate some sort of key. You're going to burn it at factory time on the chip, and you're going to have a matching crypto stuff happening on the eMMC. And so once those two things are programmed, the communication between the SoC and the eMMC can be secured. The channel that is used to have those two things talk to each other actually is Linux. All right. So effectively, if I'm in Linux and I want to securely store something, I'm going to do a request to a trusted application, effectively going in my driver, and then going into the trusted firmware, into the trusted application, and then the secure trusted application that wants to talk to hardware is going to turn around and make a request that is going to go all the way back into Linux, and from Linux onto the SD card, and from the SD card back into the trusted application, and then effectively back into Linux the other way around. So the reason for this is that the eMMC driver is not in TrustZone. The eMMC driver is in Linux. So what happens is we have a kind of deliberately a man in the middle here, but the man in the middle, be it Linux or be it somebody in RAM, can't really do much about what's going on between the trusted application and the eMMC, because these RPBM frames are secured using HMAC. So they can't actually be replayed. So even if you actually grabbed one of those frames, you could not replay the frame to actually get the information back. They're unique, all right? So in other words, it's like, think of it as SSL, right? So SSL is going over the internet, a non-secure link, but the actual conduit is secure, and that's the same kind of thing that you've got here, but effectively you've got SSL between the SoC and the eMMC. All right, and that ensures that if you store something securely in this RPMB block, then the operating system can't actually do anything about it. All righty. Yeah, example of trustee applications. If you go to this URL, you'll find some trustee applications like, you know, Keymaster, Gatekeeper, Fingerprint, and so on. And I'll show you those later on. Which gets me to the high-level operating system, namely Linux. So Linux has a whole bunch of security capabilities. I'm not going to go in depth into every one of those. There's quite a few of them that are used in Android, say LSM hooks for SELinux. SecComp is actually also used. Obviously, discretionary access controls are regular file system access controls, so they're still there. And this is the full picture of verified boot, as complicated as it may seem. So actually, this is my earlier diagram, but with just more pieces to it. Okay, so again, same kind of chain of trust here with the certificates, same eFuses, and same boot process until we get to little kernel. And then little kernel's job is to get me a image, a Linux kernel image booting, and also an AOSP to boot. So this boot image here, in the case of Android, contains my kernel image, and then the various images, file system images, be it system, vendor, or whatever else, are going to be booted also later on. So to backtrack a bit, so I already talked to you about some of those upstream pieces and such. Let me go back here and see what Google provides us. Google provides us with two things. This is the this blue-colored, light blue-colored boxes. So they give us a Linux kernel and they give us an upstream AOSP. And those two things are actually taken by the SOC vendor and then merged into a SOC vendor AOSP. Generally speaking, you will get from the SOC vendor an AOSP that has their kernel and the rest of the Android sources. And when you build that, the OEM takes that, builds that, and then signs it with their own keys, and then generates boot images, system images, and then the rest of the queue for the signing stuff happens right there. And one thing I want to point your attention to here is the fact that we're using upstream sources. So whereas the vendor stuff is highly controlled, both the Linux kernel and the upstream AOSP that Google rely on are actually going to source their own sources from third parties, namely open source projects. So whether those things are vulnerable to attack or not, that's something for you to determine. It has been there have been cases where people have tried to inject code in the Linux kernel sources and other open source projects, we'll hope that most of them were discovered. But we are still susceptible here to effectively issues that come from upstream projects. If there's a software issue in any of these blocks, then even though you've kind of secured the entire thing with signatures, it's entirely possible that you may still have some issues. And the real conclusion to this is, if you don't do upgrades, if you don't have any path for effectively making software updates, then you are going to run into trouble with all this. Another thing that the Linux kernel gives us is full disk encryption. Full disk encryption effectively allows us to intercept the calls going from the file system access to the hard disk access using the DM layer, so the device mapper layer. And so this is how we accomplish full disk encryption. One of the drawbacks of full disk encryption is it requires the system to, the user to enter their credentials at boot time for the system to be bootable. So that's why they introduced this system called file-based encryption. The idea there is when a user provisions themselves, there are directories that are created to effectively securely store that user's data, and until the user has credentialed themselves, then this data is inaccessible. And this allows effectively the device to fully boot into the lock screen, and then when the user enters their credentials, they can actually start using it. In a full disk encryption environment, the user has to enter the credential as the device boots before it reaches the home screen. So this is the drawback of this full disk encryption mechanism. Which gets me to SELinux and SEAndroid. So SELinux and SEAndroid are really hard to actually wrap your head around. And obviously in 10 minutes I don't have enough bandwidth to kind of cover it in any substantial way. But the general idea here is that there are zones called domains that are defined using the rules of SELinux. And then what you're going to say is I have this zone that is actually going to be instantiated when I run this binary. And I'm going to make rules between zone X and zone Y, which could be a file. And I'm going to say this zone can talk to this zone under these conditions. And if you don't actually have a rule that says that a certain access is allowed, then those domains will not be able to talk to each other, and you will get a permission denied. And as I've mentioned elsewhere, I spent quite some time actually. Every few years actually, would spend some time trying to understand SELinux, and every time I would hit a wall. And what I discovered really is that there is a lot of foundational knowledge or a lot of foundational concepts that are just not documented in the SELinux documentation. And in order to understand what's going on, you have to go back all the way to the sources of SELinux in the 70s and 80s to discover what's going on. So there are some pointers in this slide set, but also I've put on my website just this week class material for an Android security internals class. And there's about 300 and some slides, and there's a good chunk of of this being covered in those slides as well. There's like about 120 slides about SELinux. So if you want to get a more in-depth kind of like reach into that, then have a look at those. And in case you feel that every time you're touching SELinux that you feel a bit overwhelmed, then take solace in the fact that there are some very smart people that find it really difficult to actually use as well. So Ted Cho is one of the maintainers of the Linux kernel, and he had this to say about SELinux. He says, "Life is too short to enable SELinux." All right. And if you don't trust Ted, then have a look at what Linus Torvalds said about 10 years ago. I'll let you read that second paragraph. or at least the second phrase of the second paragraph. So Linus makes it very clear that he thinks that this is complicated, all right? And most people that in the early days of SELinux that I know that wanted to play around with it, eventually gave up. Said, okay, this is just too hard. And most distros these days don't actually make consumers or regular users have to deal with SELinux directly. So if these guys find it hard, at least I feel a bit less dumb, I guess. So as I said, by default you get denied. And the way the domains that I mentioned are defined is with the security context, which is specified with 4 fields. And one thing that I always found very hard about those rules is, why the heck are there 4 fields? And what are those 4 fields? Why is it user mode type and MLS level? I just couldn't ever figure this out, all right? And I only understood it by reading the very early research papers that were published about the SELinux work, and then the Linux security modules, and then going back and reading all the research papers that were published in the 70s and 80s and understanding the real background of that. Until I did that, for me, this was just completely unintelligible. I just couldn't make any sense of it. So there are 4 core policies in every of these security contexts. And again, the meaning of this stuff, you can only kind of understand by going back to the early days. And I'll really quickly go through this, but so one of them is a multi-level security. That is the 4th field in this thing. It's this MLS level, and is always S0 in the case of Android. So you can safely ignore this. Type enforcement. This is the one that actually allows us to define domains, and this is very heavily used in Android. In fact, that's the only one of those 4 things that I mentioned that is used in Android. And this allows us to effectively define domains, and then say those domains can talk to each other in these specific rules. And unless a rule says that you can talk to each other, those domains can't talk to each other. So by default, nothing talks to each other. And this is why you've got type TE files in the system SE policy, private and public, that effectively tell you, okay, these are the rules for the domains, and this is what operations they can conduct. The paper that describes type enforcement, by the way, is a 1985 paper, which is actually listed in my other presentation. So if you really want to understand this and the basics of it, you have to go back to read that paper from back then. Role-based access control and user-based access control are also not used in Android. It's just the type enforcement thing that is used. And here's an interesting quote from one of the Unix papers that was published about SELinux. So creating and maintaining a configuration to meet a set of security requirements and verifying that the configuration is consistent with those requirements can be a challenging task. In order for SELinux to be widely deployed and used, a collection of base configurations must be developed to meet common sets of security requirements and to allow its use by end users with no security expertise. So in other words, when they put this out, they knew it was going to be hard, all right? And it effectively is hard. So, don't despair. If you attack SELinux and you feel that you're kind of a bit overwhelmed, it is not unusual. How the security modules hooks work: you make a call, it does the regular checks, goes into the security module, calls into SELinux, it says yes or no, and this is a complete map of SELinux. It's a bit more complicated. I know I'm walking through this a bit rapidly here, but just in the essence of time, since we only have about 5 minutes left, I want to make sure that we fit as much content as possible. So the SELinux part in the Linux kernel, all right, when you make a call into the kernel, it checks with the SELinux whether you're allowed to make it or not based on the rules that are loaded. There's a user space to generate rules. In Android, it's based on the build system. You may have SELinux aware components in the user space, which themselves will understand those rules. And one thing that is very important is the labeled file system. Files in the file system will be labeled with security tags. When you access a file, it will check that tag. So if you do an ls dash capital Z in Android, it will give you the domain that this file belongs to. And this is actually going to dictate what other domains can talk to that file. It will not just be the user IDs, it will also be the domain that is tagged against that file. Which gets me to user space, how ADB works. I'll skip over this, I'll assume that you know how ADB works. App signature, all apps are signed, there is no root certificate. every app is self-signed, and therefore you can sign yourself as Mickey Mouse. The only thing precluding you from doing that is the terms of service of the store. You've got a package manager which checks those things, and you can also assign permissions, and then the package manager can then grant permissions based on signatures. All right, this stuff is a bit more documented, so I'll forgive my own self for skipping over it. OTAs. So there are two main kinds of OTAs, either through recovery or through AB updates. The idea of recovery is pretty easy. I just download an image, reboot into recovery, burn the new image, reboot again to the new image, right? The idea with AB is I want to be able to actually, be running a specific version, flash a new version into a new partition, and then just straight boot into that new partition, effectively kind of circumventing the need to go into recovery. So that's what AB stuff is. Google has on-device security that runs on certified devices called SafetyNet. You can read up about that if you want to. Continuously tests the applications, make sure that there's no viruses, and so on and so forth. Which gets me to some of the TrustZone stuff that I had been mentioning earlier. Some of the components in Android, like the key store. To securely store your stuff, it's going to go through a key store HAL, which itself is going to go through a driver, and then from the driver go to the trusted execution environment into the keymaster application. That's where you now see the result of everything that we were talking about earlier. This ensures that the secure storage for keys is truly secure, because not only does it use the trusted execution environment, but it also uses the secure storage stuff in the eMMC. Same thing goes with credentials. When you put your password in, or when you put a fingerprint in, it all goes into the trusted execution environment in order to tell you whether this is successful or not. All right, so this is all backed by everything that we were seeing earlier on. This is a bit more complicated. DRM, how is DRM enabled? Again, there's TrustZone in here. I'm not going to walk you through the entire diagram, but just remember, we are using TrustZone here to enable the chip to decode stuff that would not otherwise do or be able to do without TrustZone, right? Android for work, there's a lot of documentation about that. So again, this is something that I'll mostly skip, but if you want to do enterprise management of a fleet of Android devices, there are capabilities in Android to do that, and Google has documentation about this. And last but not least, to kind of like secure the last mile. So when a developer uploads an application into the App Store, Google has infrastructure that continuously goes around and makes sure that those apps are okay, that they don't have viruses or outdated software. So the example I give is at some point we had an app on the store that had an outdated SSL library, and we received an email from Google saying, your app has an outdated SSL library, you need to update that, or we are going to eventually delist your application. All right? And that's pretty much it for me. Given the time frame that we have, I'm happy to take questions if the time on your side permits it, or otherwise we can sign off and I can take questions by email, whatever works for you guys. So effectively, if you mess with the instruction set, can it possibly create an issue for you? Yes, it can. But the trusted execution environment is architecture such that it's not supposed to be. Let me actually. Okay, so. All right, I'm just going to switch off the. The mic from the Hangout, because that's actually feeding back. So I'll listen to your questions off Hangout, but I'll repeat them off YouTube. Okay. All right. So yes, is the instruction set susceptible to attack? It possibly is. All right. But at the end of the day, you are, kind of tethered to what ARM gives you. So the attacks that I have seen were actually not issues with the instruction set, but rather issues with the execution environments themselves. So I think there are a bunch of exploits by a gentleman called Gal Beniamini. So you can check those out. Pretty impressive stuff. Effectively what they've done is they attacked the execution environments, and they found software flaws in the execution environments, and that allowed them to, for example, be able to offload the HUK, the hardware unique key, which was burned from factory, which was pretty impressive. And so the trouble with that is the way they were using the HUK is they were loading it into SRAM, and insofar as they were loading it into the SRAM of the chip, that means a software flaw could possibly retrieve it. On some of the Apple devices, what they do is when they have a HUK, they can't retrieve it into SRAM. Instead, they can only feed it into the crypto hardware and tell the crypto hardware, use the HUK. And so therefore, you can't retrieve the HUK from the device, and then the device is secured in that fashion. So most of the stuff that I've seen in terms of hacks really is on the execution environment that is being attacked, not the instruction set itself. All right, let me know if you've got further questions. Thank you. So keep it for me. Next time I'm in Eindhoven, I'll pick it up. Okay. Thank you, guys. Thank you. All right.